Hello dear students, welcome to Pen and Paper Chemistry on YouTube.
The topic that we are now taking up is a part of electrochemistry. Under this heading, we shall be covering simple definitions of the terms like current, Ohm's law, resistance, resistivity, conductance, conductivity, molar conductivity, the relation between them and the units. I shall also encourage you to attempt a few numericals at the end of this lesson. So I hope you've got your pen and notebook ready to take down the notes for offline reference. So let's get going with the first definition. Electrochemistry is actually a fusion of electronics or electrons and chemistry. So this is a topic where we are going to use our concepts learnt in physics vis-a-vis chemical terms. Electrons flow through a conductor. The flow of electrons through a conductor causes what we call as current. Conventionally, the direction of flow of current is considered opposite to the direction of flow of electrons, right? Now, how do we define current? Denoted by I, it is the amount of charge flowing through a conductor per unit time. Charge is written as coulomb. Time is in second, hence the unit of charge is coulomb per second, or also written as ampere, A-M-P-E-R-E. You will also find the use of units like milliampere. So 1 milli is 10 to the power minus 3 ampere, denoted as capital A. What decides the amount of current flowing through a conductor? This was stated by what we call as Ohm's law. Do you remember Ohm's law from your earlier learning? Now, Ohm's law states that through a conductor, the amount of current flowing between any 2 points in a conductor is directly proportional to the potential difference across the 2 points, provided all other conditions remain constant, right? Like pressure, temperature, etc. To remove the proportionality sign, we have V is equals to IR. So we introduce a new term over here, R. What does this R mean? So R is equals to V by I. This is the mathematical representation, right? Or the mathematical value of R. What is R over here? R is known as the resistance of a conductor. The resistance that the electrons face when flowing through a conductor. You know that any conductor is made up of a large number of atoms. Now, when an electron tries to flow through this conductor, it will experience certain resistance, right? And this is measured as the ratio of V to I. R is equals to V upon I. Let's take the unit of this. R is equals to V is measured in volt. Current is measured in ampere. So we have the unit of resistance is volt per ampere, or it is given the value of ohm represented as omega. Ampere and ohm. Can you tell me a little bit more about these names? In the honor of which scientist have these units been given? Can you do a little bit of research on that and make the study more interesting? So resistance is the obstruction faced by the electrons when they flow through a conductor, and Mathematically, it is the potential difference divided by the current. Have you noted these down? Now, resistance is the obstruction offered to the free flow of electrons. What will be the reverse of resistance? That means the ability of a material to allow the electrons to flow through them easily. The reverse or the reciprocal of resistance is what we call as conductance. It is represented by capital G. Like resistance is represented as capital R. The unit of resistance is ohm. The relation between conductance and resistance. Conductance means how good a material is in order to allow the electrons. So it is the reciprocal. We have 1 upon ohm. This is per ohm. It was earlier also called as mho, but now it is represented as Siemens. Capital S. This is the accepted unit for conductance now. Let us further study what are the factors on which the resistance of a conductor depends. Can you recall from your knowledge of class 10th as to what are the factors affecting resistance? Yes, very good. First, resistance is directly proportional to the length of the conductor. So, if you have 2 tunnels to cross, so you have to go through this tunnel and the other is this longer tunnel. In which case will you face greater obstruction, assuming that both the tunnels are of the same area of cross section? Yes, you will be producing much more heat, you will be using much more energy when you are going through a longer tunnel. What are the other factors? Resistance is inversely proportional to the area of cross section of the conductor. So, if you have 2 tunnels of the same length, one tunnel and there's the other tunnel, in which case would you be expending more energy? In which case would you be facing more resistance to pass? Definitely the one with the smaller area. So, smaller the area of cross section, greater the resistance experienced by the electrons. Combining the two, R is proportional to L upon A. Now, in these two conditions, we assumed the temperature as constant because we do not want to be talking about too many factors at the same time, because we are still at a learning phase. R is proportional to L upon A, the length of the conductor divided by the area. Let us remove the proportionality sign. So, R is equals to rho into L upon A, where rho is another proportionality constant that we introduce. So, what is this rho? Mathematically, can you derive the formula for rho from the above? Very good. So, it is rho is equals to here R into A upon L. So, what is the relation between resistance and rho? We have not named it as yet. So, let us give it a name. What is rho over here? This was earlier called as specific resistance, but according to the new SI nomenclature, it is preferable to call it as resistivity. Although in some of the texts you will still find the use of the word specific resistance. So, introducing both the terms to you. It is called rho, R-H-O. Why are we calling it as specific resistance or resistivity? R is equals to rho into A by L. you know that when we have to define a term, we express it in terms of one of the variables assuming the others to be unit. That is 1. I cannot assume the resistance as 1 because it cannot be fixed as such, correct? Whereas area of the conductor, the length of the conductor, I can still define, I can still design a conductor with an area of 1 unit and length as 1 unit. That means 1 meter square and 1 meter length. So if the area of cross section of the conductor is 1 meter square and its length is 1 meter, then rho automatically becomes equal to R into 1 divided by 1, that is equals to the resistance of the conductor. So what is the meaning of using the word specific? Earlier we were saying specific. So it is the resistance of a conductor whose length is 1 meter and area is 1 meter square. So rho is equals to R and it is now called resistivity. Would you like to define its unit as well? Just put the units, the SI units of the other physical quantities. Resistance is ohm, area is meter square, length is meter. So the unit of resistivity is ohm into meter, right? Have you noted it, please? Because you will find these notes very, very handy when you go offline. And secondly, whatever is written in your own handwriting is more relatable than the notes that you get from somewhere else. Although I will be putting a link to my website where you can get the notes on this particular topic, but it is better to write it in your own hand. So let's continue with the topic. Now, just like we had the reciprocal of resistance as conductance, so G is equals to 1 upon R. Similarly, there is a reciprocal to specific resistance as well, and that is called as specific resistance or resistivity, and that is called as specific conductance or conductivity, denoted by the symbol kappa. It's something similar to our alphabet K. Kappa is the reciprocal of resistivity. So what will be its unit? 1 upon ohm into meter. What is 1 upon ohm? What did we write per ohm as? Siemens per meter, or as we know that we deal with smaller values, we also will see that the unit Siemens per centimeter is also very much used. So we've got resistance, we've got conductance, we've got resistivity, we've got kappa. What is kappa? That is conductivity. Just like we defined resistivity as the resistance of a conductor of unit length and unit area of cross section, can you define conductivity? Yes, it is the conductance of a conductor of unit length and unit area of cross section. How? Yes, just put the value of rho over here. Let's see that. So we have kappa is equals to 1 upon rho equals to 1 upon R into A by L. So if you have a conductor of unit length and unit area of cross section, your kappa becomes equal to the reciprocal of resistance. And what is reciprocal of resistance? Very good, it's conductance. So we are till now very clear on this. Now we also introduce Siemens per meter and Siemens per centimeter, right? but you should understand here we've got meter. So 1 Siemens upon 1 meter will be how many Siemens per centimeter? 1 Siemens, 1 meter is 100 centimeter. So that will be 0.01 Siemens per centimeter, right? So you have to be very careful of the unit that we are using for the measurement of length. So you may want to tabulate your learning in the form of the chart that I have put over here: resistance and conductance, definition, units, and the same for conductance as well. Similarly, you have the differences between specific resistance and specific conductance, or what is more appropriately now known as resistivity and conductivity. It would be in your best interest to note it down. Okay, let's go on further. Now, if you notice over here, what are the factors which affect the resistivity or conductivity of a material? We have the material. Obviously, each material has a fixed value for resistivity depending upon the temperature and the pressure conditions. So it is a characteristic value of a conductor: temperature and pressure. That is why while defining Ohm's law, we had said all other conditions remaining constant. So you have to be very careful about these. On the basis of their conductivity or resistivity, materials have been divided into different categories. Let us study those. On the basis of their conductivity, elements and materials have been divided into 4 categories over here: conductor, insulator, semiconductor, and superconductor. Very high conductivity, obviously it's conductors, but their conductivity decreases with increase in temperature. Insulators, low conductivity. You know about glass, plastic, rubber, which are used to make insulating handles, etc. Semiconductor, that means their conductivity is in between those of conductors and insulators, but we can increase their conductivity by 2 ways: doping, that is by adding an element from an element having lesser number of electrons or more number of electrons. That means if you are talking about an element from group 14 of the periodic table, then if you add some element from group 15 of the periodic table, you will have different types of semiconductors. You will study the details of this under a different heading. We are not touching on that. Secondly, if you notice, is another interesting point is, unlike conductors whose conductivity decreases with increase in temperature, semiconductors on the other hand, their conductivity increases by increase in temperature. A very interesting class of materials is the superconductors, whose conductivity becomes infinite below a certain temperature, and we call that temperature as the critical temperature. There's a whole chapter based on this if you are interested in learning more about it. Let's go on to the concept of electrochemistry, continuing with what we have been studying till now. Now, till now we have only been talking about solids acting as conductors. In chemistry, you know very well that we are not dealing with solids alone. We do talk about liquids and solutions which are used as conductors of current. We have already dealt with that topic where we spoke about electrolysis, right? So, what is the difference when we are talking about these two? In the case of solids, it's the free electrons which are conducting the current. In the case of liquids or solutions, it is the ions which carry charge. In the case of solids, we know, we've just now read about conductors. When temperature increases, conductivity decreases, right? Conductivity decreases. What about liquids and solutions? Oh, it's completely opposite. Temperature increases, conductivity also increases, right? If you want, you can also write the symbol. What was the symbol of conductivity that we used? Yes, kappa. Coming to the third point, you see current flows through copper wires all the time. In our homes, everywhere, current is being carried by copper wires, right? There is no chemical change that takes place in these copper wires. Yes, they do get heated up, they do melt, the circuit breaks, but there is no chemical change. Copper doesn't change in composition. Whereas when current flows through a liquid or a solution, we have discussed these earlier, we know that there is a chemical change which takes place, and we have spoken about these changes under electrolysis. Another interesting point, all the factors that we have discussed till now, like the length of the conductor, area of the conductor, temperature, nature of the material and pressure, these are the factors which are affecting the flow of current through a solid, right? What happens when current flows through a liquid or a solution? First and foremost factor which affects is the type of electrolyte you have. We shall be discussing these step by step. It also depends upon the size of the ions. Bigger the ions, more difficult will be for them to move around. The solvent and its viscosity affects the movement of the ions. A very, very important factor which affects is the concentration of the electrolyte in the solution. And of course, what we have earlier also said is temperature. Although the way temperature affects a solid conductor and a liquid or a solution conductor is opposite. Conduction through a solid is what we call as metallic conduction, right? What is conduction through a liquid called as? Yes, it is called as electrolytic or ionic conduction. Why ionic conduction? Because the ions are the charge carriers over here. Considering these factors which affect the flow of current in a liquid or a solution, we need to modify the expressions that we have obtained for conductivity, right? The most important being the concentration of the electrolyte. Because we are talking, as I said, we are going to apply the principles of physics in chemistry. Let's go ahead and do that. So we are introducing two new terms over here, molar conductivity and equivalent conductivity. What is molar conductivity and equivalent conductivity? Nothing big deal. We are talking about conductivity of a solution, right? So we are talking about kappa, but we are defining its concentration. That means conductivity of per molar solution, that means divided by molarity. When the solution has 1 mole of solute in 1 liter of the solution, that means per molar solution is what we call as molar conductivity. Same way, we have another term, equivalent conductivity. Some of the syllabi do not include equivalent conductivity, so you can ignore it. But what is equivalent conductivity is kappa, that is conductivity of a solution containing a gram equivalent of the solute per liter of the solution. That means normality per normal solution. Here you will find the two expressions. Equivalent conductivity is kappa divided by normality. What is normality? Number of gram equivalents of solute per liter of the solution. So converting the liters to centimeter cube, that helps us to define the units as well. Kappa we know is Siemens per centimeter. Normality is gram equivalent per liter or per centimeter cube of the, per 1000 centimeter cube of the solution, right? And that gives us the unit as Siemens centimeter square per gram equivalent. Similarly, to define the unit of lambda m, that means molar conductivity, is kappa, that is again Siemens per centimeter divided by the number of moles of solute, that means mole, into per liter or per 1000 centimeter cube of the solution, right? And that gives us the unit as Siemens centimeter square per mole. Makes the things easy. We are going to introduce a new expression over here. Now, we know that in solid conductors we spoke about L upon A. Do you recall that? Yes, R is equals to rho into L upon A, where L was the length of the conductor and A is the area of cross section. When we talk about solutions, so we talk about the area of the electrodes, which is such that the whole of the solution is contained between them. Now, we have different types of cells, we have different types of cell sizes, so we cannot strictly adhere to 1 meter length between the electrodes and the area of the electrodes being 1 meter square or 1 centimeter and 1 centimeter square. So we have to account for the expression L upon A, which we call as the cell constant denoted by G star. Can you determine its unit? Meter divided by meter square, which is per meter or also per centimeter. Where and how it is used is what we are going to do and what we are going to understand in the next lesson, where we shall be talking about conductivity cells and Wheatstone bridge. So do tune in to know more about these two headings and further conclude the topic based on electrochemistry. Happy studying to all of you. Take care.